Hello, Calculus 2. Welcome to Chapter 7. There's a lot of exciting stuff in Chapter 7. We're going to try to start with the idea of the area between two curves. Or between the curves. So I got some pictures here, but before I talk about that real quick, here's what we know about area and integration from Cal 1. We kind of learned that you could get the area under a curve, was the phrase, I guess. Area under f of x down to the x-axis, and you'd go from a to b, and you could do that with a definite integral from a to b, left to right. That's a left bound, right bound, lower bound, upper bound, lower bound, upper bound. From a to b, you integrate the function with respect to x. If you remember just what there was, the theory behind it was there was a little rectangle here. The width of that rectangle was dx. That's the width of the rectangle. The height of the rectangle is that y value, or that y value is the function. So when you multiply the height times the width, there's the area, and you're adding up all that as these little rectangles move from A to B. They're very thin, infinitesimally thin little rectangles, and you add up all that area, and so the total area is just the area under the curve. Well, we get area between curves if I have a bottom curve. So if I have a top curve called f of x and a bottom curve called g of x, then I do what I use the catchphrase top minus bottom. So I set up an integral and I do top minus bottom. We set up an integral from a to b, and it's the f of x functions on top minus the g of x, which is on the bottom, with respect to x. So I subtract the two functions, and that's the area between the curves. I'm going to just call it A. That's the area of that region. We use the word region for a region of area, a two-dimensional region of area. That's the region of area bounded by those curves. And we did this problem with respect to x. That the phrase top minus bottom kind of means we're doing it with respect to x, is another way to say that. That's the dx. So a couple ways to think about that is, if we were doing the area of f of x, that would be all that area. Just, if I did an integral of f of x, that would be all that area down to the x-axis, and that would include this white stuff. If I did the area of g of x as a separate problem, that would be just the area underneath g, which would be that white stuff. And if I want the area between the two curves, I would do the integral of f minus the integral of g as two separate integrals, maybe with the same bounds, which you could put together as one integral, as like we did. Or I could think of this as two separate integrals: the integral of f, and I can do the integral of g as two separate integrals. Really, I would combine like terms and do this as one integral. But I'm trying to explain that to you. Another way to explain it to you is, so that was all the area of f minus the area of g gives you what's in between. Another way to explain it is, there's a rectangle here, and the width of that rectangle is dx. That's what's telling me I'm doing it with respect to x. And the height of that rectangle is that y value minus that y value. The height of the rectangle is not that y value, and it's not that y value. It's the subtraction of those. Subtract that y value minus that y value gives you the height of the rectangle. So the height of the rectangle is f of x minus g of x. So that's one way to think. There's your height, there's your width. Well, you can do this whole thing sideways. So, these are y values. Y is a function of x. Over here I have x equals a function of y, and another x equals a function g of y. And I can do this. I use the catchphrase right minus left. Right minus left, and I would set up this integral with respect to y is the phrase, with respect to y. Sometimes, did I write with respect to x? Sometimes I just write WRT, with respect to y. With respect to y. So that means I'm doing this dy. My little rectangles are running this way. The thickness is dy. The bounds are from C to D on the y-axis. and it's top curve minus right curve, or sorry, it's top minus bottom, but I'm turned sideways. It's right minus left is what it is. So it's the right curve f of y minus the left curve g of y. So that's also area. So the area of a region in the xy plane between two curves. That's the new topic. That's all the theory behind it, kind of. We should do a problem. I think I want to erase this, so I got a little room to do a problem. So these are notes. These are in the book. You know, this is just the concepts behind what's going on. It's fun to explain the concepts. Here, let's do this problem. So we usually say, it's kind of worded long, but we say find the area of the region, find the area of the region, and then the region is defined by, find the area of the region bounded by, so then we give you the boundaries of the region, bounded by y equals x squared and y equals x cubed. I guess I could have called these, let me just call this g of x, or I'm sorry, well, I'll just stick to what I had. Sorry. I could have called them f of x and g of x like I did with my function notation. That's okay. That's all right. I don't have to. Y equals x squared, y equals x cubed. So this is a good little problem. I'd like to sketch a picture of that. I'd like to see what's up. I mean, that's how I set up these integrals. I look at the picture. I figure out who's on top, who's on bottom. I figure out my bounds, and I set up the integral, and then I do the integral. You know, so I need a good picture. So that's how this problem starts. I'm going to get rid of this. Y equals x squared is fairly easy to draw. Y equals x squared is a parabola. Your graphing calculator might be helpful. So there's y equals x squared. Y equals x cubed is that cubic function. Now the truth is I happen to know some stuff. I know that it's below this x squared. It's a little tighter to the x-axis, and it's below x squared until it crosses here. Now it's steeper than x squared. So it might be hard for you to tell, but that's y equals x squared on top, and that's y equals x cubed on the bottom. And I'm looking for this area, this little region, this little sliver of area there. I could blow that up. You can see it. You know, I'd like to know where they intersect. It's really easy to tell where they intersect. Sometimes you can just guess. When x is 0, they're both 0. Yeah, they intersect at x equals 0. You're right. Guess what? When x is 1, they're both 1. So they intersect when x is 1. By the way, their y value is 1. When x is 1, y is 1. I could have done the math. You know, that you might have to do that on some problems. To find out where they intersect, you should set them equal to each other. Watch this. If I factor, let's see, if I move the x squared to the other side, set it equal to 0, factor out an x squared, I'm left with x minus 1. I set each factor equal to 0, and I get x equals 0 as one of my answers, and x equals 1 as one of my answers. So I knew that. I got it by guessing. I could see that. But there's the actual setting them equal to each other, doing the algebra to find those points of intersection, or those x values. Well then, here we go. I can set up an integral pretty easy. Top minus bottom to get the area of that little sliver. Top, who was on top? Oh, x squared was on top, minus x cubed on the bottom. I would do this with respect to x, and my bounds are 0 to 1 on the x-axis. 0 to 1 on the x-axis. And I can do that integral and get the area real easy. You can do it if you want to. Just for fun, before we quit, we could also set this up with respect to y. I mean, if I had my choice, this was easy. This is an easier way to do it. But if you're forced to, because your teacher likes to make you work with y's, then we'd have to set this up with respect to y. We'd have to work with right minus left. Let's just try that. The picture's already drawn, and I just erased the good notes. But what you have to do is now, this right curve is this y equals x cubed. But you have to write him as a function of y, meaning you have to solve for x and write him in terms of y. So when you do solve him for x and write, x would be the cube root of y, or y to the 1/3 power, or the cube root of y. This curve here is y equals x squared, but when you solve for x in terms of y, to write him as a function of y, his name becomes x equals the square root of y. Again, the bounds are these y bounds here, 0 to 1, right minus left. I can set this up, but it's a little more confusing for students. They get a little confused. I didn't start with a very difficult example, but here we are. The area would be, again, 0 to 1, but it's a different 0 and 1. It's not these x values, it's these y values, 0 to 1, and it's the right curve, which is, I'm going to write it as y to the 1/3 minus the left curve, which is y to the 1/2. And I'm doing this with respect to the variable y. So I can integrate and evaluate and get the area of the curve. I can integrate and evaluate and get the area of that region between the curves. It'd be interesting. They should be the same answer. Of course, this looks like a little easier integral. I don't know. I wasn't really going to do both of them. I think you can handle them. I'll try this one. How do you integrate? You add 1 to the power. You get y to the 4/3 when you add 1. Then you divide by 4/3 or multiply by 3/4 minus. You add 1 to that power, y to the 3/2, and then you multiply by 2/3. That's how you integrate. That's the old power rule. And you evaluate from 0 to 1. That'll be pretty easy when you plug in a 1. 1 to the 4th, that's a 3/4. Minus, plug in a 1 there, that's a 2/3. When you plug in your zeros, those are a bunch of zeros. So there it is, 3/4 minus 2/3. Everybody knows that's 9/12 minus 8/12. That's 1/12. That should confirm that it's 1/12. You can do the math if you want. That's awesome. All right. Well, you try some homework in 7-1, area between functions. It's good stuff. I'll do some more examples.